Welcome to the amazing Cranfield University and to our event today with EBIC. My name is Toby Thompson. I'm going to be your host for the next 1 hour. We promise to finish on time, so it's great to have you with us. And if you've joined some of the Engineering Biology in Action webinar series before, you are especially welcome. You need a badge if you've attended all the previous 3 events. This is the last of this series of Engineering Biology in Action, number 4. And we're talking about rare earth elements and bioleaching. If, like me, you're not sure what that is, stick around, because you're going to find out. Not only are you going to find out, you're going to find out from some experts. So please stick with us. And if you're watching the recording, welcome. Stay in touch with EBIC and all the people that you see on the screen here. And you can continue to ask questions after the event. So if you're on the recording, welcome again. And at the very end, we're going to be talking about next steps and an amazing conference coming up mid-September in an exotic location. So if you want to know where that conference is and which exotic location that conference is at, stick around to the end, or fast forward if you're watching the recording, and you'll find out where that is. We are also today in partnership with Elemental Engineering Biology Mission Hub. So it's fantastic to have Elemental joining us too, and we have Anna later on talking a little bit about that. So Elemental, brilliant to have you with us here. I am joined in the studio. I am in the presence of greatness. Your face when I said that. Professor Louise Horsfall, all the way from Edinburgh. Yes. You travelled down yesterday or the day before?
Yesterday.
Yeah, you'd canoed like Greta Thunberg, I'm sure. So you're talking about, or you are rather, have I got this right, a professor of sustainable biotechnology.
Yes,
Tell us a bit about what you do at Edinburgh.
Well, I'm recently seconded to the Edinburgh Earth Initiative as the university's circular economy champion.
Oh, gosh.
So I'm split between being a circular economy champion for the university, as well as being professor of sustainable biotechnology, where I have a research lab, I lecture, I teach. I have a research lab where we're investigating how to recycle and recover technology critical metals.
So you self-identify as an economist, as a scientist, or a synthetic biologist?
I think I've always identified as an applied synthetic biologist or a biotechnologist.
Not just wheel spinning, but actually put it to some practice.
It's always been directed to an application, yeah.
Wow. We're going to hear a lot more from Louise coming up, but I want to introduce, if I can, our other colleagues joining us in the session here. Give us a quick wave, Danny, just to prove that you are real. And Anna, give us a wave, like a wooden wave like Danny's was there, just to prove. Sorry, it's a bit of a cheesy point there, but it's fantastic, Danny and Anna, having you with us. Danny, tell us who you work with and a little bit about your background.
Yes, so hi everyone. My name is Danny McNeice, and I am the Sustainability Manager for Pensana PLC. Pensana is a London-listed company, and we are developing a rare earth supply chain, with our focus at the moment being on a rare earth mine and refinery in Longonjo in Angola. So we're well into our construction stage, bringing online that process, and from that we're going to be selling light rare earths into the market in the coming years, in the next couple of years or so. So that's where our focus is as a business at the moment, and on that site we will be looking to mine rare earths out of the ground, and we will be looking to refine them into a market saleable product.
Wow, Danny, that's amazing. It's fantastic to have the industry angle on this too, because we have 2 academics, but you've got the practical industrial angle, and anything ESG, environmental social governance, I know you know that. Anything ESG you're also interested in too, because that's your principal role, is that right?
It is, yes, yeah. So I look after everything sustainability, from both the corporate element for the London listing, right through to our environmental and our social and community performance on the ground in Angola.
Incredible. More on that story later. We want this to be a highly interactive session, so we want questions pretty much at any time. Maybe start by saying where you are in the world. Anna, can I come to you next? And I've got to do the whole dinosaur thing. Natural History Museum. You're a research fellow at the Natural History Museum. You're also part of Elemental. Tell us a bit about yourself.
Yeah, so Good afternoon, everybody. Thank you for the opportunity to be here. I am a research fellow in applied geomicrobiology at the Natural History Museum. I don't work with dinosaurs, but I am very close to some dinosaur
Sorry,
bones,
I couldn't
and I see
resist
them
that.
every day.
So bio-based strategies for metal extraction, have I got that right?
Yes, so I look into microbial systems, so microorganisms, to extract and recover critical metals from different waste streams and from low-grade ores as well.
We got another word we want to get over quickly, bio-based technologies for the valorization of mine-impacted waters. Just briefly, what
Exactly, yes.
Valorization?
So there is another strand of the work that I develop at the Natural History Museum, is looking into recovering metals from metal-impacted waters or metal-contaminated waters that are generated within mining areas through anthropogenic activities or natural activities as well.
Wow, stick around. You've got to stick around because that was interesting. I think I just about understood most of the words in that sentence there. So just a reminder, we want your questions, your comments, your challenges even, on observations pretty much at any time that we're together in the next, what we have here, 55 minutes. So find the text chat. I'm sure you've used the text chat in Teams before now. And then just pose your question if you can. I will then put the questions pretty much to any of the speakers that you've now met. So guys, Danny and Anna, thank you very much. Stick around. I want to come back, if I can, Louise, to you. Just set the scene. If someone's in the audience thinking, I'm in the wrong webinar, I'm a social scientist, what's this got to do with me? What's the bigger scene of rare earth metals and bioleaching? What are those things?
Well, rare earth metals are one of the critical metals. So there's a whole list of critical metals. In fact, each country kind of comes up with its own list of what's critical for its industry, for its technologies, for its consumers. The UK has a list.
Oh, we're talking hundreds?
Oh no, not that are critical.
20?
No. So there's a relatively small number. I can't actually remember the exact number. And these are, the criticality is a dynamic factor. So this list changes. It gets relooked at regularly.
Every year or so, depending on what's coming up.
Well, it used to be every few years, and we went by the EU's list, and now the UK has its own list. Wow. And it's dependent on what we are using, how we're accessing them, the political landscape of the countries that we access them from, our relationships with those countries. So it has quite a social political dynamic to it, as well as there is new ores being found. So we still go out and find new sources of these metals.
Of the same metals or new metals, conceivably?
Of the same metals. Right. But if there's a new technology that comes online, suddenly it might mean that the priority for that metal that's used in it suddenly goes up. So it's such a dynamic factor. And rare earths is the one at the moment that's constantly in the media. It's the reason why Trump kept wanting to buy Greenland. It's impacted because China has all the processing, our relationship with China and the other relationships in the world with China, that criticality gets impacted when it comes to rare earths because of those relationships.
And we talked earlier on about the kind of disciplinarity, the cross-disciplinarity. So don't go thinking of it as just geomicrobiology or biotech or whatever. It's pretty much everything that you mentioned there. The political situation in Angola that Danny talked about, conceivably.
Yes. So there's all the humanities and social sciences, economics, the sustainability, and then there's the engineering of actually putting any of this into practice. There is the bio-based processes which we're advocating for, but the traditional methodologies are chemistry based. There's the physical nature of being able to break up and access these metals from the ores. So it covers everything.
So for someone on the webinar, great to have you with us again. Keep those questions coming. If someone's new to the whole topic, how would you begin to find out more about it, aside from talking to you guys?
Well, we're still trying to find out more about the topic. Certainly, I've come at it from the microbes and the metals interactions, and I've learned a huge amount through collaboration. I collaborate with material scientists, with metallurgists, and technology developers, and it's those collaborations that teach me how what I'm proposing could potentially be put into practice. So we're all learning.
We're all learning. That's good to hear. I'm going to go, if I can, to Danny, because we want to get, I think it's a fairly early on industrial perspective of this one. And we joked beforehand with Danny about what keeps Danny awake at night. Danny, I'm going to ask you that question to begin with. What keeps you awake at night in terms of industry and rare earth metals? Go ahead.
Yeah, no worries. So we did sort of beforehand, didn't we? We said that what keeps me awake at night is the 3-year-old daughter rather than the work.
I love it.
But definitely in terms of the rare earth space that we're operating in, it is a very, very challenging space. As we've already spoken about, there are quite a number of different drivers around rare earths. So you have everything right through from the growth in market demand. You have to remember these products are used in all sorts of different applications, but particularly relevant over recent years has been the model growth in things like wind turbines and electric vehicles, and the green technology side of things, where the rare earths, particularly the neodymium, praseodymium, which are in the light rare earths group, which are required to go into permanent magnets, which you'll often see spoken about in the media. And these magnets are in essence high performance magnets that go into anything that requires a high performance magnet that basically allows things to spin, which is where your electric vehicles motors come in. It's where your wind turbines come in. But also,
sorry, Danny, medical imagery as well, MRI scanners and things like that.
Yep, different rare earth group, but yes, all that sort of thing is very much relevant within the rare earth groups.
And I know you've got some pictures to share with us, Danny, but in terms of rare, are we talking about rare, or it's just costly to get out of the ground?
So the rare is nothing to do with the fact that they're rare across the world. The elements are there. It's a historic thing to do with actually, I believe, and I might have to go and check my ancient history or my naming cultures from over the years, but it's more to do with how the concentrations they're found of in the ground.
Right.
So some metals are found in reasonable quantities, easy to get at. Rare earths are found in very, very small quantities and are notoriously difficult to extract, and they become even more difficult when you actually try and separate those elements. And one of the particular challenges about rare earths is how complicated the supply chain is. So if you look at what we're involved in with our projects we're constructing in Angola, we're doing a mining phase where we'll take the materials out the ground, but we're also doing quite a substantial on-site beneficiation, on-site refining process, where we actually take those first steps to start to produce something that's more market ready. As part of that development, because of those complexities, we actually take the first 2 or 3 steps in that process. But once it leaves us, it will then go on to a number of further stages in the process. And we are looking at partners for this, for how we develop that whole supply chain. But it will go from us, it will go to another refining stage. Then it will go to a stage where it will be transformed from a separated rare earth product, so a neodymium, praseodymium product, a lanthanum product, a cerium product. They would then go through a stage where they have to be separated into metals. Typically before that, they're kept as chemical products, usually oxides. They then have to be separated into a metal. That then has to go through a process where they are effectively activated as magnets. They're then assembled, into a magnet. That magnet is then assembled into its final product, be it an EV engine, be it something in the artificial intelligence cooling industry, be it something in robotics, be it something in the wind turbine marketplace.
And Danny, I'd love
then
to.
it will go on to its final assembly.
Sorry, we'd love to see some pictures of this. I'm not sure some of the pictures that you've got are the
Yes.
Angola operations, but if you can talk us
Yes.
through some of those.
Absolutely,
And where does
yes.
where does Pensana's remit finish? Is it when then that initial processing leaves Angola? I'm intrigued.
No, so the challenge we've had, and what you can see on the screen in front of you is our project development at the moment, which is very much around developing the infrastructure on which we can build the refinery and house the workforce. But one of the challenges with that rare earth process is that because there is a lot of geopolitical tension at the moment, so you'll hear statistics about China having above 95% of the processing in that magnet stage of the process. There is a lot of talk, there's a lot of action trying to develop more politically broadened supply chains. But because the rare earth supply chain is so complex, it's very, very difficult for one company to just operate one stage in isolation, because ultimately at some point of that supply chain it will still go back to those individual jurisdictions that have those market controls. So whilst this project we're talking about will produce an early stage mixed rare earth product, we're also looking at partnerships, how we can be engaged further into that value chain. And we're also working with some of our potential end users and some of our potential midstream partners around how we can develop an integrated value chain that takes the products all the way from what we're doing in Angola all the way into your electric vehicles you have on your driveway, or the cooling equipment to power the AI data centers.
Let's see some more pictures. We love your pictures.
Yeah, no, absolutely, yes. And I mean, if then go to the next slide. So this gives you an idea of the scale of what we're doing, and this is only a very small fraction. So this is literally just the refinery and lay down areas for the project, as well as the camp that we've built for the expats to come and live in.
So the ore extraction is somewhere further away.
Yes. So if you put that picture up again. So the area, if you go back to picture 2, that's there you go. So what you can see, so the areas you can see that we've started construction, all that area across the road, that's going to be the open pit. So it'll be an open pit mine, and it'll run pretty much most of the width of that picture, all the way from the road, part way up the hill that you can see behind. And if there are any geologists in the room, you'll probably know more than I am, but it's what they call a weathered carbonatite. And it's near surface mining and extraction. So if I sent you a picture in 15 years time, that there would in essence be a big hole in the ground that we're mining the ore out of.
Weathered carbonatite. I made a note of that. Never heard those two words put together. More pictures if you can.
Yeah, absolutely. Yep. So this one is this is something that I think is very, very relevant to this discussion. What you can see in front of you now is the first stage of our earthworks for our tailings storage facility. So the tailings storage facility will effectively be where all the material that goes into the refinery that isn't part of the final product that goes off to market will be transported to. So you probably see tailings storage facilities in the news. If you read upon mining, they often come into the mix as being big ethical and sustainable challenges. But in essence, where we're really interested in the elemental and the biological potential is that the process does not extract 100% of the marketable and the saleable materials. And that's a simple fact of science at this moment in time. But this tailings, there'll be material in there that still contains rare earth materials that might be of value to the market. And that's where we're working very, very closely with the Natural History Museum on a funded project to look at whether we can use microbes or above ground trees, plants, to actually extract further materials from the tailings so that we're not leaving effectively waste material and going back to doing more mining, which then creates more impacts that I'm sure we're all aware of.
Danny, I know you got more slides, but there is a quick question if I can, and this is from Ellie. Ellie, it's good to have you with us. Thanks for your question. Are there research, or is there research ongoing into using the secondary sources that you talked about there, the recycling and the mine wastes? Where is that picture?
Yeah, so I think that there's no question that recycling, reuse, repurposing of many of these critical minerals is going to be a big part of the market going forward. And there is indeed lots of people doing research into how this can be done, recycling. One of the challenges is that the market capacity that's needed is not yet going to be servable from recycled material. So however we talk about it, and some people do want to talk about going to 100% recycling, it's going to be a long period of time before we're there. And if we pull out mining for new materials, then you're going to end up not being able to build the green technology. So if we were to cease mining for rare earths, you wouldn't have wind turbines, you wouldn't have EVs, for example. So there is research ongoing. We're certainly not just looking at how we can activate secondary sources, tailings, also looking at how we can improve process efficiency, so that for every kilogram of ore out the ground, we put more material into the market.
Danny, thank you. I'm going to stop you there because we're going to move the conversation on, but thank you. Feel free to put questions to Danny in the text chat. Danny's got 2 more slides, but we're going to come back to those if we have time at the very later on. So Danny, thank you. I want to move the conversation now, if I can, to Louise. And I know Danny mentioned there the kind of proportions between waste, and your opening slide, I know, has a scary looking statistic or proportion. I'm going to hand over the slides to you and feel free to elaborate on what it was that Danny said there.
Okay, thank you. So yes, the reason that Danny's open mine has to be so large is because for every ton, on average, for every ton of rare earth elements that we get, we are creating 2,000 tons of toxic waste.
And this graphic illustrates that tiny block on the left-hand side. I can barely see it.
Yes.
This is, you've done the maths on this.
Yes, I've done the maths. It took a while, but I've done the maths.
That is scary and disappointing, and all the negative aspects.
Yeah. So it's, we need these metals. We absolutely need them for the green technologies and for the green transition to happen. But it means that we need to find ways to be able to mine them sustainably, as sustainably as we possibly can. That might mean bringing new technologies on board, as Danny said, making sure that we have the efficiency where we're getting everything out that we possibly can. And also, it means that we have a duty to keep whatever we have extracted within the economy, which is what kind of the question was alluding to. We also have that mission to be able to keep things within a circular economy.
A duty to the future of humanity.
Yeah, absolutely. And also because everything that we keep within the economy means we don't have to mine for it again. So it is that balance, because at the moment, with the increasing demands for these metals because of the technologies that we're using them for, we have to do both, as Danny said. We can't just recycle what's already there, because we haven't been reliant on these metals for very long.
We didn't know we wanted them.
No, we didn't. If you move to the next slide, I've got some examples of some of the technologies that we're using these metals in. When it comes to the rare earth elements, they're very much going into wind turbines, they're very much going into the motors in electric vehicles. So they're absolutely vital for the green transition. But broadening that out a bit, we've also got a lot of other technology critical metals. And I guess to some extent this particular figure is slightly misleading in that it's got very high to very low, but that's still very low of a critical metal.
And it's complex,
So,
and it
yeah,
literally is
it's
complex.
incredibly complex.
More complex than this even.
Yes, but even those that are very low are still critical.
A
So
definition of
it's-
critical is an economic definition, a social definition?
Oh, it's a very complex definition. That's where it's about our demand and also the supply risk.
So Pensanas of this world and Danny aren't determining what's critical.
No.
Society determines what's
Yes.
critical.
Yes.
Right.
Yes.
Feel free to come back down if you want to. You've got some more fantastic slides. Do carry on with those.
Yes. So basically, the diagram that I just showed, it was produced as part of a report from the EU, which said we have to be able to supply these metals as sustainably as possible, keep them within a circular economy. And this is just a kind of reiteration of what a circular economy is. We have to reuse, remanufacture, recycle as much as possible instead of the linear economy where we take, we make and we throw away. And unfortunately, the UK is incredibly linear. I think it was about 92.93% linear.
Oh, no.
We throw an awful lot away.
Just the UK?
No, globally we are, but
Bad.
we are bad. The UK we're all bad. We need to be more circular. And if you move to the next slide. We believe that there's opportunities for microbes to help us with this circular economy. And when it comes to metals, whether it's from an end-of-life technology or whether it's from an ore or a mine tailing, low-grade
Ellie
ore,
loves mine tailings.
yeah, then we've got mechanisms by which microbes are able to leach out the metals, often quite selectively, and get the metals into a solution. And these are some of the examples by which it does that. Next slide, please. And my work has this kind of balance to it in that we do the bioleaching, but also once that metal is in solution and we can bring in here chemical leachates, industrial waste, contaminated waters, we also then look at how we can get it out of solution and into a usable form. So that's part of the metal processing. So we don't just think that we can leach, we can process the metals in a selective way as well. We can produce minerals and even metal nanoparticles by the microbes selectively turning that liquid metal into, this dissolved metal into particles.
Who's the we in that
extract.
previous sentence? We are doing this. Is that academia or is that Danny? Who's the we?
I meant my group, my research group,
in
we,
Edinburgh, yes.
but there are other researchers out there doing this as well.
So,
and there are other methods of being able to selectively recover those metals too, not just by precipitating.
So you're finding ways to refine, to take it out of the solution, to refine, to then hand over to someone else in terms of technology readiness level to do.
Yes.
But you're researching that area as well.
Yes. And one of the examples which isn't about rare earths, if we move to the next slide of, sorry, no, I've paused here.
Go on. Who are these people?
This is an example of all those nano or microparticles that we've been able to produce.
What are we looking at?
Lots of those different metals. So these are all bacteria that have transformed the dissolved metal into a particle. So you can see examples of these particles, and lots of these include critical metals. If you move to the next slide. So we're using this within a method that we've developed to be able to use bacteria to recover the metals from lithium-ion battery cathode material. So it's part of the recycling of lithium-ion batteries that we're using in electric vehicles. And we've got a method by which we can recover the manganese, we can recover the nickel and cobalt. And once we've done that, we have a solution that has lithium left, and that can go into current lithium processing technologies for reuse as well. So we're looking at how we can, that recovered metals can also be reused as cathode materials.
Incredible. We want your questions. Please, in the text chat, put a question to us. As complicated as you can make it be. Louise is happy with complicated questions. I have a question, first of all. And And it was to do, it's kind of, I'm rebirthing my inner Danny, in terms of how ready is this? In terms of commercial applications, how ready are we talking in terms of technology readiness level? Is it all in the lab? Or are we coming out of the lab and actually doing stuff with it?
So with regards to this recovery method that we have, we've got it to 30 litres from real battery material. But yes, the next challenge is scaling up. It's scaled up really well so far to 30 litres. Our next challenge is getting it to 300. And actually, at the moment, the challenge for that is getting the cathode material to be able to do the process at 300.
There's not enough cathode material, or what?
It's just not as easy to get as you would think. But, you know, electric vehicles, you know, they're in use. People don't want to hand you the battery to work on. Also, you have to do the disassembly, which is very technical, and we don't want any kind of fires or problems happening. So we'll park that, because we're here about rare earths. That was just one example of how we're moving forward, and how these technologies are potentially being implemented. But we've also, on the other side of things, with bioleaching, that's already been done for a very long time at a very large scale in countries such as Chile when it comes to copper.
Oh, wow. Say more. That's a standard process now. There's nothing new about that.
I think certainly in Chile they would call it a standard process, because yeah, it has been, it's just absolutely massive scale, and there's not a huge amount of new technology developments within it. It's working, it's established.
I've got a question, but feel free, Danny, to come in if you want to. How does bioleaching, as we've talked about it here, as you've talked about it, compare to conventional hydrometallurgic processes? Are we talking as super efficient? Because you've got hydrometallic, you've got pyro metallurgy as well. Or is it a way more efficient way of doing it? We don't know yet.
It's a different way of doing it.
Different way of doing it.
And certainly when it comes, it's definitely different to pyrometallurgy, incredibly different. But the hydrometallurgy, it's almost a subsection of it, but it depends if those examples of how you bioleach that I kind of included, sometimes it's exactly the same as hydrometallurgy, because actually hydrometallurgy might use organic acids. And organic acids are produced by microbes. We have industrial production of organic acids. So we would just say, well, why not use it directly instead of having a big vat and then purification and then getting the organic acid and using it. So there's definite crossover with hydrometallurgy.
Brilliant. Did you have one more slide? I'm not sure if you finished the slides there.
Yes, no, I had.
You're done. Great. Again, questions, please. And Ellie, we're looking to you for a question. Anna, if I can come to you and tell us your angle on this. You've got a geotechnology or a geomicrobiology angle on it, but from what you've heard so far, just to start your presentation, where would you see you come into this?
Yes, no, I actually need to thank Louise for all of the setting the scene, because that is pretty much what I do as well. So I would like to say that I am also one of the we are doing this, because we use slightly different microbes, or we are trying out in different minerals, but the grand finale is the same. We want to achieve the same thing. And well, at the Natural History Museum, as you mentioned before, Toby, I am one member of the Elemental Mission Hub, which is one of 6 mission hubs funded by UKRI. And the focus of Elemental is to develop technologies for environmental processing and sustainable recovery of metals. And within Elemental, my role in there is to look at bioleaching of mine wastes, but also electronic waste, and then come up with bioprocesses that are more cost efficient, more sustainable, But as Louise mentioned, there are many challenges around that as well. And I want also to highlight the project that we have together, also funded by Elemental, a business interaction voucher that is my partnership with Danny, is looking and University of York, also part of Elemental, looking at microbes and plants that can extract metals from the tailings that Danny is going to have to put in that massive pond that he showed in one of his images. How can we continue to extract what wasn't extracted during the main process? So we also have a project together to look into that, which is very exciting. We've just only started, and we can't wait to see what results we're going to get from there.
I love it how, Anna, you say you just got to come up with this. That is thousands of brains working extraordinarily hard. But yeah, more on that in a second. I know you've got some slides. Talk us through some of your amazing looking slides.
Yes, so if I can get to the first slide, please. Thank you. And Toby, if I may, every time I give a presentation, I try to highlight also the role of the Natural History Museum as a research institution, not only as a museum full of dinosaurs.
Thank you. I stand corrected.
We do have many more things than dinosaurs. So we currently house over 80 million specimens of natural history, and that goes from planets, meteorites, to dinosaurs, to plants, to insects, to microbes, and that covers everything. But apart from that, we're also a research institution, and we have over 1,000 science-based visits per year to this South Kensington site, to our facilities and our collections. We also host PhD students full-time within the beautiful building of the Natural History Museum. And we have imaging and analysis facilities, molecular labs, collection facilities that allow this partnership with many other research institutions, academia, and industry, which is the case with Danny here. And we always have, across all of our research scientists and our research themes, externally funded projects, both from academia, but also government, and many other ways as well. If I can go to the next slide, please. We can actually talk about what we are here to talk about. And these two illustrations, I think it brings together very nicely what both Louise and Dan have talked about. And the one on the left-hand side really just highlights all of the different types of metals and other elements that are required to make a smartphone, that little thing that we use for many hours every day, and we have billions of them in the world. We require many different metals, and as technology advances and our phones get better, we require different metals. Again, pointed out by Louise before, decades ago, we wouldn't hear much about rare earth metals, rare earth elements. And now every other piece of news on TV is talking about supply chain of rare earth elements. But a bit more broader than that, than our smartphone that we use every day, we have the renewable technologies, that those then require a significant amount of different metals, not only rare earth metals. And if you can look, I hope you can see that from the screen. If we pick out copper as one of the metals, just as an example, it is one of the base metals that is utilizing almost all of the examples highlighted in the type of energy there. And then if you look at the wind, the renewable energy by wind, it is one of the technologies that requires the highest number of metals. And not all metals are being highlighted in this chart. So the list goes on. And if I can go to the next slide, if no questions.
Nothing so far. Go ahead.
Okay, so again, we've talked about it. So what are the challenges? And I think this, again, marries really well with what Louise was saying about the criticality. So here is a diagram on the left where you see what elements, what metals are critical, what are not so critical, and the ones that are not critical at the moment. And you can see that it is a relationship between the importance to the renewable energy, the green transition, but also the supply risk. And bringing back what Danny said as well about having one country monopolizing the market, not only China is the largest producer of rare earth products, they also have the largest reserves of these specific metals. And if you look at the charts on the right there, Brazil is also a big player in having the reserves. However, it only contributes to 1% of the global production, because that refine step doesn't happen in Brazil. It is sent then to China to get processed and refined there. So these challenges are not just the geopolitical issues and the number of critical metals that start to creep up on this annual list now, but also the grade of the ores aren't the same as a century ago. So we are dealing with low grade ores, which makes the extraction more energy intensive, and it generates a lot more waste, which then in turn can have environmental and social impacts through just the processing, but also the mining impact within the community and the environment. And again, Danny mentioned, we don't recover 100% of everything. And a lot of the critical metals are still left in the tailings or in the waste or the waste materials. And that brings in also the urban mining into the equation, where we are looking at, there are all of these metals that we are not currently using, and they are wasted. So all of these challenges bring then the strong case for alternative technologies, for cleaner, more selective, and economically viable, hopefully, to extract not only rare earth elements, but as Louise very well pointed out, this is also true for other metals as well. And next slide, please. These are some of the ways that engineering biology, through both elemental and EBIC as well, all of the efforts of bringing engineering biology to today's research, is to solve at least some of these challenges. Some of them it's out of our control as a researcher, but there are so many other things that we could look into to overcome some of these challenges. And when I say engineering biology here, I mean using microbes, enzymes, bio-based process engineering, synthetic biology to extract, to recover, to separate, to monitor, to recycle. It really covers a great deal of options. And because the topic of this webinar is bioleaching and biomining, I will focus a little bit more time on the bioleaching box there. Obviously, as Louise said, it is a technology that has been applied industrially for over 50 years, and it is very well established for copper and gold. There are less examples for other base metals like nickel and cobalt. There has been many industrial operations also for uranium, but it still hasn't revolutionized the mining industry. So many people still don't know what bioleaching actually is. And in terms of engineering biology, there are a few things that we are looking into to overcome some of the limitations of the technology, which, for example, often it is slower than some of the conventional methods like pyrometallurgy, for example. And the scale up is also, there are quite a few challenges regarding scaling up, especially for rare earth elements. So in terms of engineering biology, there are different things that we can do to tweak what nature already does, so we can improve the recovery rates, and we can generate less waste or even reprocess waste that has been produced previously. And I would like to highlight an example of a startup in the US, our colleagues from the US. The startup is called Regen, and they are focusing their efforts into using a modified strain of gluconobacter oxidans to extract rare earth elements from rare earth ores using bioleaching, but with synthetic modifications that allow that process to be quicker and to recover more rare earth elements. So this is what we are here to talk about. The lab successes exist, but we do need a bit more help to getting it out of the lab. Other ways the engineering biology can help. One of the things that Danny has mentioned, the separation of rare earth elements is incredibly hard, incredibly costly, and whoever cracks that, it's in for a good run. And biology can help in many ways in this aspect by using, for example, there's some lanthanide binding proteins that is very selective and will only carry the rare earth elements and leave all of the other metals behind. Engineered peptides, enzyme-assisted processes. So there are many different ways that we are trying to overcome the challenges. And by we, in this case, I mean the scientific community. I don't do any of that.
Good to get clarity on that. Thank you. You have one more slide.
Yeah, well, I know very good friendly colleagues that do that, and they're very successful, but I'll leave them to do that. But then also other things that the engineering biology can help is recovery from secondary resources. Still back in the previous slide, if we can go back to the other one. Thank you. And again, what Louise mentioned a few times as well, the valorization of waste, of materials that need to go back to create that circular economy. And that includes not only products that we as humans once consumed, but also the waste materials from mining processing. And another one interesting as well is biosensing and monitoring, finding biological systems that all of these things, by the way, already happen in nature. We are not creating anything out of thin air. These processes already happen. We are just putting them in a scenario where we allow the microbes to essentially, we just look after them very well like children to make sure that they make the best of their job within a certain scenario. If that is precipitating metals, if that is leaching metals, if that is recovering, separating metals. So there are many different ways. Many of them, however, are still in low TRL levels. Not many of them have reached yet industrial applications, but we are not too far because the demand and the need is there. And my last slide.
Just briefly, if you can, Anna, we haven't got very long, so I want to get a conversation
That's fine.
going.
And I think Danny can jump in on it as well if I say anything wrong. So there are the drives from industry. So the decarbonization is one of them, cleaner and secure supply chains, local processing, being able to mine and refine and create the project locally, the need for technologies for complex resources, conventional methods are becoming less attractive, and regulation. Obviously, these are some of the drivers, but the mining industry and the manufacturing industry also, they are very cautious. They are aware of the limitations, and I think that's one of the reasons why things have not evolved as quickly as we would have hoped. And there is to do with economics, there is to do with the complexity of the feedstocks, and in some cases the slow kinetics and the scale-up risk. And I think that obviously bio-based technologies are not going to replace mining and processing, but it is a technology that will complement so we can together get to the demand that we need, deploy the technologies that we want, and use our phones even with more technologies.
I'm just thinking, how many phones have I got stuffed in drawers with all the gold and everything that's in them?
Exactly, yes.
Anna, thank you so much. Danny, I wanted to come back to you if I can, because your name was mentioned there several times, not least of which about collaboration between industry and academia. I don't know if you want to comment on what Anna's been saying there.
Yeah, I think, as I've said up through the conversation, partnerships are so important with this. And no matter how you frame it, and there's been different drivers even in the 5 years I've been working for Pensana, whether it be green economy, ethical finance, or the more recent drives towards security for energy supplies, security of supply for defence, etc. The drivers change, but ultimately, at the end of the day, people want minerals. They want minerals as affordable as they can be, and they want guaranteed supply, which is as safe and secure as it can be. And partnerships with academia and the research is great, because if there's people who are happy to do the projects, look at all these different ideas, spend the days and days and days in the lab, trialing out all these fantastic and wonderful ideas, if that sows the seeds of the things that can help to improve the efficiency in the future, or to help keep the cost down, or drive a more effective industry, then the partnerships are great. Really, really are, and a really good way for us to work.
I love how you're mirroring each other there, Anna and Danny. Thank you so much. But I was left, Louise, with a worry there. That's the picture that Anna paints. It's extraordinarily complex. Is that not a worry? Everything is involved.
Yes. That's why it's also still an academic subject, because it requires study for all those interactions and all those different in-depth knowledge of different subject areas, and how it all works together and how it all comes together. So
frustrations, what are your frustrations? Why can't it burst out of the lab into Danny's area?
Well, I mean, I'm hugely grateful for Danny being here and the collaboration that's happening. But I think something that as a limiting factor that Anna didn't allude to is necessarily, is that mining companies, she said, they're kind of got their embedded technologies, but they've also got their embedded expertise and their comfort zones. And there aren't a huge number of them that come from the microbiology background. So it's not necessarily the first area that they turn to. So EBIC, Elemental, having these hubs of expertise and the resources to then be able to reach out and have these long-term conversations and establish these relationships that make these partnerships that actually value each other's expertise is incredibly important.
New generation maybe of miners, and I saw that we have, was it Chris Bettinger? Look at your chat and you'll see something from Chris Bettinger on that. Anil's got a question here in the few minutes that we have remaining. With bioleaching in Chile largely conducted in open environments, how do you see implementation of genetically engineered microorganisms in industry? Or is their use going to be left to contained bioprocesses? I'm going to start with you first.
Yeah, there's lots of complexities here. We have very strict containment regulations. The processes that I'm developing are in contained environments, and that would allow them to be employed in the UK. But yes, there are different ways to be able to use genetically modified organisms, microbes within an environment. Each country chooses its own regulations. We are about to have a whole paper published on what should, how this could be implemented, but also there are technologies available that create mutations which do not fit that genetically modified organism. Organisms, microbes mutate naturally. The sun is a mutagen. They evolve. If you can adapt them to that situation. It might mean that they still bring the processing that you want them to do, and you've taken them from one environment to another and give them time to adapt, and then they can still do that process but within that new environment, and that doesn't necessarily require that genetic modification. The reticence against genetic modification is because we believe in the past it's been less precise than it is now. There are regulatory changes that are in the process of happening when it comes to the Precision Breeding Act, where that's for plants, but that precise changes are more understandable, they're more reliable, and it may be that in future, as long as things can be shown that they then don't evolve further, who knows?
Who knows?
There's lots of different questions around this subject, and I'm feeling like I'm getting outside of my expertise, and it gets a bit icky because, as I said, certainly what I'm doing is in a closed environment.
Exploring boundaries is exactly what science is about. Danny, very briefly in the seconds that we have, GM released into the wild sounds really dangerous, right?
I think, as with everything, there are a number of environment, social, governance risks, and I think this is another area where it's really important for business and academia to work together. You'll probably all know that most of what we do is heavily regulated, some of it through legislation, some of it through voluntary standards, and I think listening to what's been said there, it's very much around, we would only do this if it's best practice, if it's well understood, because the risks to a business of taking something on, regardless of any potential financial reward, the reputational damage, the regulatory fines, the damage from getting these things wrong can be exponential. And we only have to look at some of the previous tailings failures where tailings dams have failed and you've had thousands of fatalities in a matter of minutes just because an engineer didn't build a wall to the required standard. So this, as with any other area, it would only be done if it was in the right environments with the right safety barriers, the right protections. And of course, it's people like Anna, people like Louise, who are experts on this, who would be heavily involved in writing the guardrails to allow this to be done safely and effectively without those risks that you've articulated.
Danny, thank you. That's reassuring to hear. Just very briefly, Anna, the last question to you in a minute. Breakthroughs. What breakthroughs are we looking at in bioleaching and the areas that you're working in?
Within engineering biology, for example, things that we are seeing within our research community, rare earth elements they are the group where most of efforts are going into. So there has been advances and like I said, breakthroughs in the separation of rare earth elements, which is one of the most important aspects of rare earth mining nowadays, and extraction as well. So I think the focus currently has been on rare earth elements, and the most advances have been made in the processing and separation of these metals.
Brilliant.
And if you compare that very quickly with COVID vaccine, we needed a vaccine. That vaccines take 10, 15 years to make, and we had one done in 2 years. It depends on the demand. It depends where the interest is.
So it's possible. Sorry to cut you off there. We are running out of time, but it's possible.
That's okay.
You paint a very positive picture. We have run out of time. It's a real shame. We can be talking about this as we have with the other 3 events forever. Get in touch with any of the grown-ups that you see on the screen here to find out more information. It just allows me to say that this will continue. We want you to have EBIC membership, so please apply and get EBIC membership. Also, there is, and I mentioned this, and you're going to be there, I'm sure, the conference coming up in September. Chris, if you can put that back on the screen there, 16th and 17th of September. And I mentioned an exotic location, Southampton, which is fairly exotic. Those of you not in the UK, I would say that's exotic.
It is from Edinburgh.
Exactly. If you're in Edinburgh, as Louise is, or North Yorkshire, as Danny is. So please, registration close is at the end of August. So please, if you're interested in what you've heard today, and you'll find out more at the conference, book onto this conference, and you're going to learn an awful lot more. Thank you so much, Danny and Anna, for joining us today on what's been a very detailed and super complex conversation. So thank you very much indeed for sharing your expertise. Louise, thank you very much indeed for joining us and coming all the way down from Edinburgh. The producer today was Nicola Heaven and Crystal LaCour-Perdue. The assistant producer was Archie Gomez. The studio managers were Chris Ripley, Robin Hackett, and Marco Gomez. Sorry, it's the last conversation that we've had here. My name is Toby Thompson. Thank you very much indeed for watching, and stay in touch with the EBIC. Thank you.